Hi. In this video, we will learn about vector operations for the vectors in the plane. Okay, so these operations, the operations that we will learn, can be studied from two different perspectives. One is algebraic, and the other one is geometric. When we say algebraic, what we mean is that we will work with components, and I'll tell you how these things work in the in the terms of the components. Geometric, well, I have to show you through some drawings and things like that. Okay, the first operation we have is vector addition. Vector addition, so we have two vectors, u and v. U is u1, u2, and v is v1, v2. Then we add these two things, we will get a new vector, u plus v. The sum is a vector, again in the plane, but algebraically, meaning that the components of this new vector are given by, so the first component is sums of the first components. The second component is sums of the second components. Well, that's it. So you add the first components and add the second components, put them in the corresponding components, and then that's it. How about the geometric meaning of this thing? So if I have two vectors u and v, let's say u is here, v is somewhere here. What is the vector u plus v? Well, u plus v, there are two ways to do this one, and one of them is very natural one. If you see uv vectors as displacement from the tail to head, summing basically, or adding two vectors basically tells us the total displacement. It means what? It means that if I put u, well, u takes the tail to the head, and then I can place v in a way that its tail is the head of u. Then, well, I see that the final displacement means that the initial point that we have and the very terminal last point that we end up after going through u and v is this point. So u plus v basically tells us the total displacement. Well, the way I did this one is called the head to tail. The rule. So basically you put the tail of the second vector at the head of the first one. But there's also another version of this, which is, okay, when you have u and v, you can place them in the plane such that they start from the same point. So their initial points coincide. Then you can make a parallelogram using these two. The diagonal starting from their initial point is the vector u plus v. And that's what we have for parallelogram rule. both of them give us the same vector. In other words, the result of both of them have the same direction and same length. But they basically come from different philosophy and they look different. Okay, so that was the first operation. The second operation is called vector multiplication. Scalar multiplication. I just have to write this again. Scalar multiplication. Well, in this book and in all linear algebra courses, when you deal with numbers, not vectors, you call them scalar. Let C be a scalar. Means that it is a number. It doesn't have components. It's just one number. And U be the vector U1 and U2. Then CU is a vector. It's a scalar multiplication of U by C, which algebraically is given by this. So you multiply, so it's a vector, so I need to use the square bracket, and you multiply C to the corresponding component. C to the first component, C to the second component. So that's what algebraically the scalar multiplication mean. How about the geometric meaning of that? So if I have U like this, then when you multiply U by a positive number, C, the result will be a vector which has same direction, but its length depends on C. So has same direction, but its length is C times length of U. So you multiply length by C, whatever C. If it is 2 times. If it is 0.5, half of the length. But the direction is the same direction. How about if C is negative? If C is negative, the vector U, let me just start again by vector U here. Vector CU, do that, okay. Oh, I am supposed to do this one for a negative C. Since C is negative, the direction is going to be opposite. So it will have opposite direction. Opposite direction. Well, means what? Means that it will go the other way around. How about the length? The length will be again C times the length of U. So the length has C times the length of U. But well, you need to tell me that, okay, C is a negative number. If you multiply negative number by length, you will get a negative number. Length of C, you cannot be negative number. Yes, you're right. That's why we need to put the absolute value of that. And well, that's what the geometric picture of scalar multiplication look like. Well, there is a special case of this, which is called a negative vector. Negative vector is when C is a negative 1. So U is a U1, U2. Then the way we denote it is negative U. This is a vector minus U1 minus U2. And well, what is a geometric picture of that. So if you start with u, negative u, well, first of all, it is multiplied by -1, so it will go the opposite direction, and it has exactly same length because absolute value of -1 is 1. So let me just write this: opposite direction, same length. And well, when you have the negative vector, you can use that and define vector subtraction. Vector subtraction. So we have two vectors, u and v. When we say u minus v is a vector which the way we define it is this: you add, we know how to add two vectors, so I'll define it based on addition. So add the vector to the negative of v. In other words, this will give us u1 u2 plus negative v1 and negative v2. In other words, the components, basically you subtract the corresponding components and put them in the corresponding spot. Well, when you have this thing, basically, then you can, this definition, you can define what is, you can see geometrically what does u minus v mean. Well, why? Because if this is u and this is v, what we can do is that, well, we are trying to find u minus v. U minus v is sum of u and negative v. We know negative v has the opposite direction, same length as v. Then when we have this thing, now we need to add this and that. Use the parallelogram rule here, and this will give us what we are trying to say. This is u plus minus v, which is minus v. Well, if I take this guy, so let me just do this, take this, and then, oops, and then just shift it, so this is here, shift it here, you will see that, well, my drawing is not good now, I can notice right away. This will be the vector which goes from the head of v to head of u. So this is u minus v. In other words, the rule that we have is this is u, this is v, u minus v. It formed a triangle using these two ones, and the direction of u minus v, u is the head of u is the head of u minus v. That's how you find this thing. Well, the operations now are done. So 3 operations that we wanted to learn. There are a few remarks that I will add to this, and then we will finish video with some examples. First, remark 1. This is the most important remark of all of these. First thing is that look at the algebraic operations of these vector operations. All of them, so subtraction, you subtract corresponding components. Negative, you negative all the components. scalar multiplication, multiply the scalar to all the components. Adding, you add the corresponding components. All these operations are done what I use as component wise. So all the above operations are done component wise. Adding, you add the corresponding component. Subtracting, you subtract corresponding component. Scalar multiplication, you multiply C to all the components. And that is a very key point for us, because that is how we generalize these operations for higher dimension in the next video. That's the first remark. Remark 2 is, well, you see, when you multiply a vector by a constant, so scalar multiplication, at the end, these two vectors, cu and u, doesn't matter if u c is a negative or positive, cu and u are going to be parallel. And that is why we call two vectors parallel if one is a scalar multiple of the other one. So let me just write this one. Two vectors are parallel if one is scalar multiple of the other one. So in other words, there is C that you multiply to one of them, you get the other one. Well, I have to be a little bit careful. This scalar multiple, we need to make sure that C is not 0. If you multiply 0 to a vector, you get 0 vector, which doesn't have any direction. It's a very strange case. Okay. So that's another thing. Parallel vectors means that these are, one is multiple of the other one. And there's a third remark. This is an interesting one. Remember that when we had two vectors, 2 points, A, B. So recall the vector A, B. Well, if A is a point with a x1, y1, and B is a vector x2, point x2, y2, then vector D AB has components y2, x2, minus x1, y2 minus y1. And well, this is kind of related to the vector subtraction. Why? Because x2 minus x1 and y2 minus y1, this is like, okay, we're subtracting components of the vector x1, x2, x1, y1 from x2, y2. This is exactly the same operation. The end point minus the starting point, the terminal point minus the initial point. But these vectors, we know that these are position vectors of A and B. So position vectors. Remember, what is the position? Position vector is a vector from the end point, from the origin to that point. So this will be OB minus OA. What does this say is that basically